Hello class, welcome to the first lecture of Introduction to Material Science. This lecture focuses on categories of materials. There are four major classes of materials from the viewpoint of material design and application. Those are metals, polymers, ceramics, and composites. And composites being any kind of hybrid of the other three categories, which gives the best of categories, not the worst of. We'll review those along with the material selection process, both from an application service environment perspective in terms of understanding how to transform specifications and environmental characteristics into material properties that you need, and also from the other side, what I'd call the push side, where we look at composition and structure of materials and what type of properties that combination is likely to provide. And both meet in the middle at material properties. We'll compare properties on an order of magnitude basis across material classes, looking at the class-to-class range, the intra-class range, focus on strengths and weaknesses of given classes, and also look at special advantages of composites for giving, again, what any one class of material can't in terms of property combinations. And we'll give a particularly interesting example of the importance of processing on properties, something that's very visible. Before we get into individual classes of materials, I need to let you know that the main difference in material classes is provided by chemical bonding. Material classes are basically a manifestation of the different types of chemical bonds that are inherent in those different materials. Those include, for those of you who remember your chemistry, metallic bonding, which basically consists of discrete nuclei in a delocalized sea of electrons. So charge is neither directional nor localized. Then you have covalent bonding, which is common at the other end of the spectrum, where charges are very directional and associated with a particular nucleus. Ionic bonding, which is partway between, where you have fixed charges that are associated with one another. And of course, composites can draw from any one of the three. Okay, four major classes, starting with metals with their delocalized charged metallic bonding. They tend to be very strong, ductile. Again, that ductility is given by an ease of deformation for a given application of stress, and that is because those delocalized electrons allow things to move at an atomic and microstructural level quite easily. They're very stiff because the bonds, in spite of being mobile, they're very strong. But on the flip side, they have a fairly high density. So if you're looking at lightweighting applications, that can be a detriment. The delocalized electrons give them very high thermal and electrical conductivity. Again, could be a plus or a minus depending on your application. And that same kind of charge delocalization also makes them opaque and reflective, not because of scattering, but because the electrical component of an electromagnetic field, light of any frequency, can interact very easily with those delocalized electrons on an electronic scale and not be transmitted. Going to the other end of the spectrum, polymers. These are typically organic, although a silicon-oxygen structure is fairly common in the case of silicone polymers. These have covalent bonds, so electrons are very localized and associated with a given nucleus. They have a particular structure to the bonds. Again, for you chemists who remember your sp3d type hybridized orbitals, these form the basis of polymer structures, which we'll be learning about later on in the course. Compared to metals, they have much lower strength. They can either be ductile or brittle, depending on the particular polymer and processing. They tend to have very, very low stiffness compared to metals, but on the flip side, they're much lower density. So again, if you're looking for a high strength to weight ratio, polymers, in spite of their low strength, might actually be the winner. Again, because of the covalent bonding, those electrons can't move easily, and so they tend to have very high thermal and electrical insulating qualities, or high resistance thermally and electrically. This is not an absolute. It is possible to have polymers with delocalized electrons, different type of bonding, and those will have higher conductivity, but generally not nearly as high as metals. And they tend to be optically translucent or transparent, with the amount of transparency being mostly dictated by scattering. and that is in fact one of the ways you can tell amorphous from crystalline polymers is the degree of transparency from the scattering on grain boundaries. Not an absolute, but a general rule of thumb. Third category is ceramics. These tend to be inorganic, and they are more generally ionic or ionic character bonding, although the oxides and carbides will be more covalent character. So they're going to share some of the properties of polymers and metals in terms of the nature of bonding. They tend to be compounds of metallic and non-metallic atoms. So again, oxides like aluminum oxide, or carbide, silicon carbide, iron carbide, which is very important for steel making. Nitrides and sulfides, again, good for fillers and coatings. The most important characteristic of ceramics in terms of design limitation is lack of fracture toughness, or they're very brittle. They can't absorb very much mechanical energy per unit volume of material. This is very limiting in how they can be deployed, since they don't resist propagation of a crack. So they can't resist high rate loading, thermal shock, etc., which tend to be quite prevalent in most engineering service environments. On the flip side, they are stiff and strong. They're non-conducting, both electrically and thermally. And it's not shown on this slide, but one of their greatest attributes is very high thermal resistance. So not only do they not decompose or melt at a fairly low temperature, they retain all their other properties at a very high fraction of their melting or decomposition temperature. So if you need something that stays strong, doesn't creep, doesn't lose its properties at high temperature, especially over time, ceramics are a great choice. And last but not least, what if you need something that's stiff but low density? What if you need something that's strong but can withstand high temperatures? You can combine materials, usually with deliberate processing methods, to form a hybrid. And this is the fourth category, called composites. And again, it's a hybrid. It's a combination of the other three material classes, and it is intended to give properties that you cannot get with any one category alone. If you have one material that's a bulk all by itself, it's known as a monolithic material. Composites are not monolithic. They are hybrids structurally and compositionally generally. Okay, material selection process. So if we start at the top portion of this, with applications and service requirements, that's what's sometimes referred to as a pull, where the need for a given new part or the requirements of a new service environment, or more recently new regulation, will exert a pull on the material designer and say, hey, we need a new material that can help us design a new product, or we need to meet this new government regulation and be less toxic or be more recyclable, or we need to be cheaper so we can sell in a more competitive market. So as a materials engineer, you will be coming up with a new material or selecting materials with properties that allow you to meet service requirement needs. So this will again start over on the application side. Maybe there's a new product. You want to put out a product, your company needs a product enhancement to be more competitive. It's always easier to market your product if it's cheaper. This will lead to a set of service requirements. If you are in supply chain, for instance, this might come in the form of a customer's specifications. Our part must do this, be this strong, this fracture tough. It must resist this temperature for this much time. It has to be so transparent to a certain amount of light frequency, certain type of light frequencies, for instance. Corrosion resistance could be expanded into general weathering and durability. What environment are you going to use it in? Is it being used in a high temperature processing tank, outside on a bridge, over the ocean? Possibilities are endless. Weight, light weighting being very important for aviation, for aerospace, anything you launch into the air. Weights or mass, more specifically, and density are very important even for inertial applications. Cars don't fly, but they become much more efficient if they have lower mass, because you have to accelerate and decelerate them, and there's a lot of energy loss associated with acceleration. So making a car lighter makes it more efficient. There's a lot of other applications where lightweighting becomes important from a cost standpoint, even looking at raw material supply, say to a construction site, or decommissioning after the fact. Sooner or later you got to move all that mass, and moving mass is energetically expensive. Which brings us to sustainability, and that's in bold for a reason. It's a bit of a new concept when you think in terms of service requirements, but it's very far-reaching in terms of its scope and the way it will impact our choice of material properties or the need for certain material properties. Sustainability is a catch-all for what used to be called cradle-to-grave or life cycle material and engineering design. And this means that you look from the very earliest point in your supply chain, your raw material acquisitions, sourcing, where are you going to find it, how are you going to get it, drilling for the oil that's used to synthesize the polymers, mining the metals that you'll use to make the metallic raw materials, etc. Same thing with ceramics. Where are they coming from? How far do you have to transport them? How much energy, environmental impact is inherent in primary, secondary processing? How many transportation steps? What kind of waste streams are emerging from each one of the different processing steps? And then, of course, end of service life disposal. Can you reprocess it? Can you repurpose it? Can you recycle it? How toxic is it to dispose of for how long? So all of these have high, sometimes initial financial costs, but definitely high societal costs. And even if those societal costs are not captured in, say, a request for bid or a customer specification, they are very frequently captured in government regulations and international regulations, which you will have to meet if you want to do business. So it's a very real consideration, and it's a big driver of the material properties that you will need to obtain. Okay, so how do you obtain them? Well, your material properties come from two places. One is composition, which basically encompasses the three basic material classes, metal, ceramics, and polymers, and from structure. How those atoms are put together, directionality, how the bonds are arranged, multi-phase structures versus single phase, how much void, grain boundaries versus single crystals, crystalline versus amorphous, etc. And then the macro structure that would be involved in forming a composite. How do you get structure? Processing. You very rarely use a material the way you dug it out of the ground or the way it came out of a synthesis plant. So quite often an introduction to material science class goes under the terms of materials and processes because the two are so integrally linked, and that's through structure. Structure of your material is what is obtained by processing, and it's what allows your composition to come to bear on the properties that you need to meet your materials or your part service requirements. So let's take a look at some of those material properties across our four classes and see how they compare, what the ranges are, and what the inherent strengths and weaknesses of the different classes are. We're going to start with density, since hey, that's pretty common to everything, and again, lightweighting is such an important part of so many different industries. If we start over on the left-hand side of the diagram, the y-axis, we can see that this is in grams per cubic centimeter, and we range from 0.1 to 40 grams per cubic centimeter pretty much across all four classes. So that's, give or take a couple of orders of magnitude, 2.5 orders of magnitude spread. Fairly respectable, but we'll definitely see a few material properties that have more. Now, in terms of the losers, we can say from a lightweighting standpoint is metals. Metals definitely top out the density scale, with the highest for platinum group being above 20 grams per cubic centimeter, and the lowest for magnesium and aluminum coming in, more or less even with the more dense polymers. And as a caveat, magnesium alloys definitely are problematic from an incendiary standpoint, and from the standpoint of strong materials that you can use in most service applications, they are definitely the lowest density metals you can get. So this is a pretty generous range for the metals category. Ceramics are definitely less dense, and that's mainly because you have lower atomic weight components. There's a lot of oxygen, nitrogen, carbon present in, give or take 50 atomic percent. That tends to be the origin of the lower density there, but they're still higher than polymers. Polymers' lower density comes both from the fact that it's lighter elements and it is a less dense structure in general. The polymer molecules cannot pack as closely as a ceramic or a metal. Composites definitely are the winners in the density category, both from an absolute standpoint and from the fact that the highest performance in terms of other properties, which we'll see, still come in at the bottom end of all three materials. So in terms of density, metals, you better be getting something else for them in terms of properties to effectively pay for the high density, which will cost you, even if you don't have a lightweighting application, will cost you in shipping and shipping disposal associated costs. Okay, stiffness or modulus. This is an indication of how much a material deforms under a given stress or load. We'll definitely be talking about this very specifically in Chapter 7. This is a major design criteria for things that can only move so much given a known loading or vice versa. And you can see from this that there's a good reason to put up with the high density of metals, because for the most part they are all very, very stiff or high modulus materials. Even your lowest density metal, magnesium, still has a fairly high stiffness. So you don't pay much in stiffness to go to a lower density metal. They're fairly tightly clustered and they're all at the high end. Speaking of high end, what's the general range? Much bigger spread than you saw with density, almost 6 orders of magnitude spread. And if you look at polymers, this is where you pay for that light weighting. You've got the better part of 4 or 5 orders of magnitude between your average ferrous alloy and polyethylene, which is much less dense. So, definitely can't have it all unless you go with a composite. Composites are always a bit more expensive, but this is one example of where they're worth it. You can see that, say, carbon fiber reinforced composite, CFRC, the higher stiffness end of the composites range, is overlapping with the higher end of metals. And if you go back to density, you can see that it's probably an order of magnitude less dense than the average structural metal here. So you definitely get the best of both worlds with composites in looking at density versus stiffness. Okay, well, stiffness isn't everything for mechanical properties. You don't want it to yield and you don't want it to break. And a property that characterizes both of those is tensile strength. So again, looking across categories, metals win in the strength category. Ceramics are also very strong. They've got a different weakness, the fracture toughness, which we'll get to next, but nonetheless they are very strong. Polymers are the losers on strength as they were on stiffness. And as was the case of stiffness, composites give you the best of both worlds. So we're now seeing two big advantages of composites from a lightweighting standpoint. Low density together with high strength and stiffness. And total range across all categories, much lower range of tensile strengths versus stiffness. We have only a couple of orders of magnitude range. So just keeping in mind of how much difference there can be. Stiffness definitely has the greatest range class to class of materials. Okay, fracture toughness. Energy per unit volume that a material can absorb. And this is what will give us our crack stopping capabilities, thermal shock, prevent us from catastrophically failing in service. Metals are another winner. This is another way that they pay for their very high density. They're very fracture tough, again coming from their delocalized electrons. Here's where you can see ceramics really failing. Ha, pun intended. Hopefully not, because we'll design them correctly. But they do in fact have the lowest fracture toughness of any material, overlapping with polymers surprisingly. And there is a difference for the fracture toughness low fracture toughness of ceramics versus polymers, and we'll look at that quantitatively later on in the course. Ceramics are very high strength, but have very low ductility, and fracture toughness is effectively a combination of those two properties. In fact, it's the area under the curve defined by those two. Polymers are the opposite. They tend to have very low strength, but tend to have high ductility, but nonetheless the combination is low. So if you need to impart a lot of energy, especially in a short amount of time, ceramics are definitely not your best choice, and polymers can be problematic. And again, if you need the best of in terms of lightweighting and fracture resistance, composites are a good choice, but unlike strength and stiffness, they still lag your more common engineered metals by within an order of magnitude. Speaking of order of magnitude, again, we've got a bigger spread. Not as big as stiffness, but definitely bigger than density and tensile, looking like 3 orders of magnitude. So stepping away from mechanical properties, let's look at a material property that has a huge range of properties, magnitude of properties across material classes. Electrical conductivity in ohm meters, ranging from 10 to the 8th for metals, which within its own category spans 4 orders of magnitude, and down into the 10 to the minus 18 for your most insulating ceramics and polymers. So we're talking the better part of 20 orders of magnitude from your best electrical insulator to your best electrical conductor. And semiconductors sitting right in the middle due to their electronic band structure. So this is an example of where the interclass range of properties definitely beats any intra. That said, ceramics definitely span quite a large range in and of themselves. Not that I would use them for an electrical power transmission cable, but if you're looking at how well they insulate, there's definitely a big difference between a partially conductive defect structure in a ceramic that's bordering on being semiconducting and a very high dielectric strength, fully insulating ceramic. And again, this comes mainly from the electronic structure, and in the case of the polymers, you can also see that there's a broad range, again, due to that how delocalized are the electrons in those covalent bonds, mainly covalent. Okay, so far our description of classes has arisen mainly from composition, with composites as a class constituting the effect of processing and structure on a macro scale. This slide gives you an idea of the effect of processing in its own right. These are 3 samples of aluminum oxide. They are all the same thickness, even though it's not really apparent from the slide. And you're seeing a difference in translucence, optical properties that are solely, or that is solely a factor of processing. As a fairly brittle ceramic, aluminum oxide is processed by what we call a powder metallurgy type of processing. You start with a submicron, fairly pure powder and subject it to high heat and pressure, and the need to reduce the energy associated with the surfaces of that powder will drive what's called sintering densification. The powder will actually fuse, form necks, and eventually the voids between the particles will be driven out, and you can obtain a fully dense structure. Well, the first part of that process, the partial densification, leaves you with a structure that's effectively continuous aluminum oxide. It's solid, it has some reasonable mechanical properties for a ceramic, but it has a high void fraction, so it's effectively a composite, if you have it, of aluminum oxide and air. So it is a multi-phase structure. So light that impinges on it will bounce off of all of those aluminum oxide air interfaces, scatter, and not penetrate. So you get a very opaque material. It also has very, very poor fracture toughness, even for a ceramic, since all of those pores act as little crack starters, which we'll discuss later as well. If you get rid of all those voids, you attain a certain amount of translucence, and you see that in the middle. Well, you do that by the same process that you started sintering with, but you just continue it. You continue to densify the structure, adding heat, adding pressure, eliminating high surface energy surfaces until all you have are aluminum oxide grains impinging on each other. So you now have one phase, but you have a lot of grain boundaries. All of those aluminum oxide crystals aren't lined up in the same direction, and so the light can bounce off the grain boundaries. This is a multi-grain structure. It's translucent, not transparent. Much better fracture toughness. If you get rid of all the grain boundaries, such that you have a single crystal, there is nothing to scatter the light. Light goes right through and you have a completely transparent structure. So if you look at it from the standpoint of optical transparency, say you need a lens or you need a window on a light source, not all aluminum oxide is the same. You definitely want to process it into a single crystal. So this is our example of processing matters, depending on the property you want. So in summary, any set of circumstances. That's really the heart of the class. And then for those of you who will be going into materials or materials heavy disciplines, it's important you will be doing the push. You'll be developing new processes, possibly developing new materials, which will then be available to designers, buyers, businesses, and will create new applications and new business opportunities. So that is it for our material categories and classes lecture. We will start again on our next topic, which is atomic structure and chemical bonding. Thanks very much.